All right, we're gonna look at the complex zeros homework. And so for number one, it wants us to use the rational zeros theorem to find the zeros for that big polynomial we got going on here. So again, normally you want to look at it and just see if it's factorable, like regular methods that you know, but just glancing at it, it doesn't look like it. So we're going to start by listing the possible rational zeros. So remember, that's looking at the factors of the constant term. So in this case, the negative 16 over the factors of the leading coefficient, which is 3. And so these are going to be just the possible ones. So when you think about 16, its factors are going to be 1 and 16, 2 and 8, and then we have 4 and 4. And so it's both the plus and the minus of all of those. And then this is all over the factors of 3, which is nice. It's just 1 and 3 since 3 is prime. Okay, so we're looking at all the different combinations made by those fractions right there. So I'm going to start by trying like 1, because I like using the smaller, kind of easier numbers first. So when I try 1, I'm going to put the leading coefficients from up above again. And again, my goal in order to find a 0 is to make sure that my remainder is 0 with that synthetic division. So I bring down the 3. 3 times 1 is 3. We get a 2. That's 2. That's negative 34. Multiplying, that's negative 34. And so then, let's see, negative 34, that's going to get us 26, positive 26. And then we multiply that, and it's not going to get us a 0 remainder. So then let's just try 2, kind of counting up there. 2 happens again because we have both the 2 and the 1 there. But the lead coefficients. And let's see, we'll bring down a 3, that makes 6. Combine those, we'll get 5, then that'll be a 10. We'll get a negative 26, which will make negative 52. Gets us 8, that's 16, and then 0. Woohoo, we found one, yay! All right, so we know that 2 is a 0 because we have that remainder 0. Now the polynomial that's left over here, it has 4 terms, and I can write it out. This is our constant, then 26x, 5x squared, and then 3x to the third. Now when you have 4 terms, you can always try and kind of factor that by grouping, because again, our goal is to find all the zeros. Now there was a little hint in the directions for this little part. It said to find 2 zeros. And so what's happening is we're not able to factor that our traditional way, so we're going to have to find another 0. And the way that I'm going to do that is because I'm basically trying to break up this guy now. And so if I'm going to break up that guy, trying to do this factoring using synthetic division, I'm going to put those coefficients here. So 3, 5, negative 26, and 8 to try and break up that guy. I'm going to try 2 again, because often if we have a 0, it ends up being repeated. Like we can see that it has a multiplicity higher than 1. So let's just try for fun and see if it works. So when I try 2, let's see, that will be 3. We'll have 6. That will be 11, 22, negative 4, and woohoo, it did work. So what that means then is that we have 2 2s. Then this part right here is going to be a nice quadratic. I'm going to bring this down. This will be 3x squared plus 11x minus 4. Now notice there's lots more spaces here, so you might have been doing a lot more synthetic division in order to find it, and I was kind of lucky that I found it right there. So this is the leftover polynomial, so we know this times x minus 2, because of that 2 being a 0, gets us that polynomial. Then because we know that this 2 was a 0, we're going to put in another x minus 2, and this would get us our original f of x function. Now we would try and factor the 3x squared plus 11x minus 4, just our regular way. It's a quadratic. So if we want to try and factor that, if you do your AC method, that'll be a negative 12, because it's 3 times negative 4. And the number that multiplied to negative 12 and add to 11 would be a 12 and a 1, make the 1 the negative since 11 is positive. If you continue factoring by grouping, I'm going to make sure I don't run out of room in that little box. I'm going to break apart the middle term with the 12x and the minus 1x that I found. And the 3x squared still comes along, and then minus 4. And so by grouping, the first two terms have a 3x in common. We're left with x plus 4. The second two have a -1 in common. We'll be left with x plus 4. And so we know that it is factoring by grouping nicely because we have that same term, x plus 4. And then our leftovers, a 3x and a -1 will go in there. And again, you could have done it by guess and check. You don't have to do it by this AC method and grouping. But factoring this, it will become x plus 4 times 3x minus 1. And I'm going to keep those x minus 2 factors. You can write it as squared. So we have factored that polynomial all the way. And so to list the zeros, we already know that x equals 2 is a 0. And x plus 4 is a 0, or is a factor. So that means -4. And then 3x minus 1, that would become a +1 over 3 because there's that coefficient you have to divide by. And again, the factored form, just writing it neatly here, would be x plus 4, 3x minus 1 times x minus 2 squared. Alrighty. For part 2 here, they want us to look at this new function, f of x, and they're giving us that 4 plus I is a 0. So using the complex conjugate theorem, we also know 4 minus I is a 0. And so two corresponding factors would be x minus that 4 plus I. Put it in parentheses there just so we can have it sitting there. And then x minus the other guy, which is 4 minus I. Now, f of x is a degree 3 polynomial, so that means that it wants to know how many zeros does it have. It would have 3 zeros. And so there's a few different ways that you can go about finding that third one, because again, we already know 2 of them, and set up right now for us to do synthetic division. So we're going to do 4 plus I, and we'll put the coefficients of that polynomial. And this is where we're going to have to do a little bit of operations with complex numbers, which is totally fine. We'll drop down our 3. Now 3 is going to multiply by 4 plus I. That's going to make it distribute. That would be 12 plus 3i. Then combining these two together, we're going to combine the real parts, which will make a -16, and we'll have plus 3i. Then we're going to have to take this and multiply it by 4 plus I. I'm going to do that just down below to make sure I have enough room, because that's going to have to be distributed. And so there's going to be a lot of terms that pop out of that. -16 times 4 will make a -64. -16 times I is -16i. 3i times 4 is going to be a plus 12i. And then last, 3i times I is going to be plus 3i squared. But we know that I squared is equal to -1, so really this is -3. So what that leaves us with is a -67, -64, -3 is going to be -67. And then we have -16i plus 12i, that's going to be a -4i. Okay, and we'll combine those together and back in that synthetic division. And so 83 minus 67 is going to be 16, and we'll have -4i. Then we're going to multiply that again by 4 plus I. I'm going to go down and multiply that. So we're going to have that 16 minus 4i times 4 plus I. So 16 times 4 is 64. 16 times I is plus 16i. And then we'll go to the -4i times 4i is -16i. And -4i times I is -4i squared, which this becomes, again, because I squared is -1, this will become a plus 4. So here's kind of nice because the 69 and -69 cancel out. So we have 64 plus 4, which is 68. So going back to my synthetic division, you can see that gets me my remainder of 0. Now I don't want to write the polynomial with those complex coefficients there, but because I know 4 minus I is a 0, I'm going to break that apart. And I'm going to write these coefficients right down here instead of writing the polynomial and just do synthetic division, because I know that that conjugate is a 0, so I should get a remainder of 0. If I don't, then I did something wrong. So dropping this down, if we bring 3 times that 4 minus I, again, it has to distribute. We're going to get a 12 minus 3i. We combine these together, our i's cancel, we're left with -4. Multiplying that, again distributing, we're going to get a negative 16 plus 4i, which you can see gets me the 0. Okay, so the last little bit here, that polynomial that we got, this leftover, is again 3x minus 4. So when it says find the last 0, we have the last 0, we'll set that equal to 0, and that will get me x equals positive 4/3. Okay, so that's the last 0, and then it says to write the whole thing in factored form. So we already know 3x minus 4 is a factor, so I'm going to write that out. And then we had those complex ones. So we're going to have a 4 plus I and a 4 minus I. Now that's getting super messy. Let me write that out a little bit neater over here just so we can see it. So again, there's 3 factors. 3x minus 4 is the last one we found after doing all that synthetic division. And then the other 2 are our complex conjugates, and it's going to be x minus minus. We have 4 plus I and 4 minus I. We're not having to multiply any of that out. That is our factored form for our f of x. And that finishes up that one. All right, flipping over to the next page. Again, we're starting off with a big polynomial here that can't be factored. So if we're going to try and find the zeros, first thing is listing those possibles. So we're looking at the factors of 15 over the factors of 2. And so we're going to get plus and minus 1, plus and minus 15, and then plus or minus 3, plus or minus 5. That gets us all of our our factors. And then on the bottom, plus or minus 1, plus or minus 2. So all those different combinations will get us those rational zeros. So again, we're going to start, and I'm going to make a guess just because I kind of seen this problem before. And here's my guess. I'm going to use 3. And so let's see if that works. 2, negative 11, 27, negative 41, and 15. So we bring down our 2. That makes 6. We get a negative 5. That's negative 15. We'll combine those. That's 12. We'll get a 36. That's left with negative 5. And then negative 15. Woohoo! We get our 0. Now again, the polynomial that's left over here, it does have 4 terms, but there's no way it's going to work by doing some sort of grouping. So we're going to have to break that down some more. So we're really looking at, just to kind of give you a heads up, this polynomial f of x, we just saw that 3 was a 0. So it can break apart to be x minus 3 times the polynomial represented in here would be a 2x to the third minus 5x squared plus 12x minus 5. And so what we're trying to say is, okay, well, let's try and break up this polynomial some more. Now, it can't factor by grouping. You could check, but it doesn't. So we're going to have to use that rational roots theorem again. And you could list the factors of the lead coefficient and the constant term and go through that way. So I'm going to use the factors of negative 5 over the factors of 2, and so we're going to get plus minus 1, plus minus 5, and then plus minus 1, plus minus 2. And so when we do synthetic division, again, you didn't have to write this down. You could see in here what the coefficients are for our polynomial. So I'm going to, because I'm running out of space, scoot down here. So that will be a 2, a negative 5, 12, negative 5. And so I'm going to make a guess. So let's make a guess. I could try 3 again and see what happens, because we had that repeated 0 earlier. So I'll take 2, that'll make 6, 1, 3, 15, and then 15 times 3 is not 5, so that's not going to work. Okay, and so let's see. I just chose 3 for that repeated 0, but as I'm looking, I'm like, that wasn't even an option. Let's use 5. So we have 2, negative 5, 12, negative 5. So we get a 2, that's 10, 5, 25. Okay, this is getting way too big. So that's not going to work. Let's see. We did 5. Okay, we could try 1. So I'll put 1 in there. 2, negative 5, 12, negative 5. So that's 2, negative 3, negative 3, 9, 9. Nope, that's not going to work. Okay, so then we can start looking at fractions. So I have a 1/2, so let's try 1/2. So we have 2, negative 5, 12, negative 5. So 2 times a half is going to be 1. A negative 5 plus 1 is negative 4. Negative 4 times a half is going to be negative 2. let's see, 12 minus 2 is 10. 10 times a half is 5. Woohoo, that works. Okay, so we have found 2 zeros. So let me cross off that second 3. That didn't work. So the number 3 worked, and the number 1/2 worked. And so again, what we were finding with this last guy here is that 2x squared minus 4x plus 10 times, well, 1/2, that's coming from x minus 1/2, or I kind of like it better to write 2x plus 1, or not plus 1, minus 1, just so we can work with whole numbers, okay? So that's that kind of breakup of that polynomial, and then we also have x minus 3, which makes our original f of x function. Okay, so using the coefficients of that remaining quadratic, we can try and see if that's factorable. And you could check that out. What multiplies? Well, actually, there's a GCF of 2, so if we pull that out, we can see what happens. If we factor 2 out, we're left with x squared minus 2x plus 5, but there's nothing that will multiply to 5 and add to negative 2, so we know that doesn't factor. But it was helpful to take that 2 out, because if we're going to try and solve that equation, using the quadratic formula would be the next step. And if it's factored out, it's kind of working with smaller numbers. So remember, x equals negative b plus or minus the square root, b squared minus 4ac all over 2a. And so our a is 1, our b is negative 2, our c is 5. And you could use quadratic formula using the 2, negative 4, and 10 coefficients. You'll just have to simplify your radicals at the end. So it's kind of nice if there was that GCF. So if I plug in, and again, you can check if you did that, just make sure that it simplifies to be the same answers that we get here. So negative b would be a positive 2 plus or minus the square root. Negative 2 squared would be 4 minus 4 times 1 times 5 all over 2 times 1. So x is equal to 2 plus or minus the square root. Negative 4 times 1 times 5 is negative 20. So we have 4 minus 20, which would make a negative 16 all over 2. Well, if you have that negative inside, we know that we're going to have an imaginary number here. So this comes out to be 2 plus or minus 4i all over 2, which actually this simplifies as well a little bit more. We can do it a couple different ways, but if we write it in that form, a plus bi, this is 2 over 2 plus minus 4 over 2i. But that's really 1 plus minus 2i. So those are going to be my other 2 zeros. So if I'm going to list them all, I have that x equals 3, I have the 1/2, and then I have the 1 plus 2i and the 1 minus 2i. So again, in factored form, I'm going to have x minus 3 for that first 0. I'll have 2x minus 1 for that second 0 of 1/2. And then I'm going to have, they don't look pretty, x minus, we'll put 1 plus 2i and 1 minus 2i. Okay, so again, it doesn't look that pretty, but it has been factored into a product of linear factors. All right, this last one, it wants us to write a polynomial of lowest degree with zeros of negative 4/3 with multiplicity 2, 1/2, and we have this last thing that says f of 0 equals 48. So for this negative 4 over 3, that makes me think of x plus 4 right away, because that would get me that negative 4, but because we're dividing by 3, that would get me that coefficient. So you could check that. And it's multiplicity 2, so it's happening twice. Similarly, for the 1/2, it's a positive 1, so I'm going to use negative 1 here, and I'm going to write 2x. That way it would divide by 2. So this is my function, but it's getting maybe stretched or something. This is just an extra thing to let us know if we're going to have a different lead coefficient. So I'm going to write an a in the front, and basically our goal is to make sure that f of 0 will equal 48. So if I plug a 0 in here, again, we're trying to check on a, that's going to be 3 times 0 plus 4 squared, and then 2 times 0 minus 1. So our first parenthesis here, that would become a 4. 4 squared is 16. So we're going to have f of 0 equals a times 16 times, in our second parenthesis, 2 times 0 goes away, so we just have a negative 1. And again, our goal is to equal 48. So on the left side, this a times 16 times -1 is really negative 16a. And we're saying that we want this to equal 48. So our a is actually not going to be a 1. If we divide, it looks like a has to be -3. So our polynomial will be f of x equals -3. That's replacing that a part. And then we have those factors that we had mentioned earlier. And they meet that requirement that if you plug in a 0, you would end up getting a 48.